Okay, so we go back to our BJT sheet, and this time we're looking at our voltage gain for simple sets here. So we are interested in these right here. Okay. So the first thing we want to do is we want to look at the names that they use. And in order to do that, they're called common and then one of the terminals. And the terminal that they are called is the one that isn't used. So you see in this case here, we have one point connected to the base. And here we have one point connected to the collector. So the one that doesn't have a connection to it is the emitter. So this one is going to be called a common emitter, or a CE stage. Let's look at this next one. So this next one has a connection to the base and a connection to the collector. So this one is also a common emitter. Now this one has connected to the emitter and a output connected to the collector. So this one has an emitter connection and a collector connection. So this one is going to be called a common base. This one has a base and this one has an emitter. So this one is going to be called a common collector. So we have a common emitter. This one's actually called a common emitter with emitter degeneration. This one is a common base and this one is a common collector. Okay, so now we want to derive the voltage gain equations for these basic stages. Okay, and in this one and this one, we have an RO because there's no VA. And in these two, we're setting VA to infinity to get the simplified case. Okay, so let's start with the first one, which is our common emitter. Okay, so with our common emitter stage, that configuration looks like this. So the first thing that we do is we draw our small signal model. And this one has a GMV pi, and it has an RO. So then we go over there and we start connecting things. So right here is our emitter. So we connect that to ground. Over here is our base. And we put our input source there. Okay, and then over here we have our output. And then we have a resistor that goes up to a DC voltage source. And we're doing a small signal or an AC analysis, though, so that becomes a ground. Okay, so then we want to redraw this and flip this one down. So we're going to call that RC, and this is RV out. Okay, so now we see these two are in parallel, so we can just make a parallel combination, and then all of this current goes through that parallel combination. So we have V out equals you see that this current is going around that direction. So this is equal to minus RC GM, RC in parallel with RO times GM times V pi. And then we come over there and we see that V pi equals V in. So our V out over V in equals minus GM RC in parallel with RO. Okay, that's our first case. So we are done. That is the equation for our common emitter. Okay, now we're doing our common emitter with emitter degeneration, and that's going to be very similar, except now we're going to have a resistor down here. So if I just grab all of this, and we are going to come in here. The only difference is now we have an emitter resistor down here, which is called RE. Okay, so now this one makes it a little bit messier because now we see that V in is not equal to V pi. So we have to figure out how V in and V pi are related, because we see right here, oh, except for this, in this case, we are getting rid of our RO. And our RC goes to ground, not to the other case. So this looks like this. Okay, and then when we do all of that, the way that that makes it nice is that we see that V out is equal to minus RCGM V pi. So this is good as long as we know what V pi is, but V pi is not equal to V in, so that's where it gets a little bit messier. So we have to come in here and do a node voltage. So we're going to come in here and we are going to call this one, let's just call it, since it's the emitter node, let's just call it VE. So what we see here is now we're just going to do a node voltage right there. So we are going to go equal to VE over RE plus VE minus V in over R pi minus GMV pi. And then we also equals 0. And then we also see that V in minus VE is equal to V pi. And we are trying to get rid of the VE, not the V pi, so we can also have VE equals V in minus V pi. Okay, so then we're going to take this and plug it into that equation. So we have V in minus V pi over RE plus a minus, you see that we rearrange this a little bit, and we get that V in minus VE minus V in equals minus V pi. So this is going to be minus V pi over R pi minus GMV pi equals 0. So now we're just trying to solve for V pi. So we have V in times 1 over RE equals V pi times 1 over RE plus 1 over R pi plus GM. Okay, and then this is equal to V pi times 1 over RE plus GM over beta plus GM, And so that means that this is negligible, so we make that go to 0. So then what we have now is we have that V in equals V pi times 1 plus GMRE by just multiplying through by the RE. Okay, so this means that V pi equals 1 over 1 plus GMRE. And now we just come back to this part here, plug in for our V pi. So we have V out equals minus RC times GM times V pi, which is equal to minus RC GM over 1 plus GM RE. And typically what we do to get it in the form is we're going to divide the top and bottom by the GM. So V out over V in equals minus RC over 1 over GM plus RE. And this is our gain equation for our common emitter with emitter degeneration. Okay, so now we are going to do our common base configuration. So in this configuration, first of all, we see to make it a little simpler, we're not including an RO. So like we did before, our first step is drawing the small signal model. So we start with our standard small signal model, R pi, V pi, GM V pi. There's no RO. So this is our collector, this is our emitter, this is our base. So let's start with the base. The base is just going to be some DC voltage, biasing voltage, so that's just going to be ground. And then we're going to have an RE. And a V in. And then this is our V out, and then we have an RC, and that goes up to a ground. So we have to redraw all of this circuit because I got grounds up here on the top and grounds over here. So let's redraw this to make this a little bit simpler. So we have, here is our R pi that goes to ground. Here is our RE, here is our input source, and then here is, let's move this down a little bit, and then we have our dependent current source, which goes to our V out, and then we have a RC that goes all the way to ground. Okay, so again, from before, we can see that I have a current loop that goes like this. So now my V out equals minus RC GM V pi. But in this case, V pi, again, is not equal to V in. So we have to figure out how V pi is related to V in. Once we figure out how V pi is related to V in, then we just plug it in here and we get our gain. So again, we're going to have to do a node right here to figure out how all of this is going to work out. So again, let's just call that my VE node like we did before. So we have VE over R pi plus VE minus Vin over RE minus GM V pi equals 0. Okay, and like we did before, we can see that this VE is related to that V pi. So in this case, my VE equals minus V pi. So I can just plug that straight in, and so then I have minus V pi over R pi minus V pi over RE minus Vin over RE minus GM V pi equals 0. So now we're just going to put our V pi's and our Vins on opposite sides. So Vin times 1 over RE equals minus V pi times 1 over RE plus 1 over R pi plus GM. And just like before, this term is negligible because it's much, much smaller than my GM. Okay, so now we have Vin equals minus V pi times 1 plus GMRE. Okay, which means that my V pi is equal to minus Vin over 1 plus GMRE. And then we're just going to plug that straight into there. So now we have V out equals minus RC times GM times a minus Vin over 1 plus GMRE, which is and so that means that my V out over my Vin equals RC times GM over 1 plus GMRE. And lots of times we divide through by the GM to get it in the form that's on our little table. So that's equal to RC over 1 over GM plus RE. Okay, so that's done with our common base. Now we are going to go and do our common collector. So this is our common collector. The same thing. We're going to start with our small signal model. In this case, we are leaving the RO in. Let me do this first. And again, collector, emitter, base. So then we come over here and our input is connected to our base. Our collector is now just connected to a voltage source, so this is just ground. And then we have a emitter resistor to ground, and our output is labeled right here. So now you can kind of see that I have a ground up above, so we want to redraw this so that our ground goes down. So we have this. So here is our V in, which is connected to ground. We have our R pi. We have our RE. We have our RO. We have our current source, which is going away from ground. So that looks like this because we flipped it over. And this is my output right here. So you can see we have everything kind of set up like that. And my V pi is right here. Okay. So what we have to do now is we're just trying to calculate what my V out is. So I just do one node voltage right here. And so we have VO over RO. And you can see that these two are in parallel. So we're just going to combine them in parallel just to reduce this a little bit. Okay, plus VO minus V in over R pi minus, sorry, now it's plus, no, yeah, minus GMV pi equals 0. Okay, so that's the 1, 2, 3, 4, 1, 2, 3. Okay, and then we have that V pi equals V in minus VO. So we can plug that in to get everything in terms of VO and V in. So we have VO over RE in parallel with RO plus VO over R pi minus V in over R pi minus GM times V pi, which is V in minus VO, equals 0. Okay, so now we put all of our VOs on one side, all of our V ins on the other side. So we have 1 over RE in parallel with RO plus 1 over R pi plus GM equals V in times 1 over R pi plus GM. And just like we did before, anytime I have a 1 over R pi plus a GM, this one becomes negligible, this one becomes negligible. So we rewrite this to see what it looks like. Okay, looks like that. And then we want V out over V in, which is going to be equal to GM over GM plus 1 over RE in parallel with RO, which is equal to, I can divide the top and bottom by my GM, 1 plus, oops, where did I lose my, okay, so to put this in the form that's in our table, what we're going to do is we want our RE and get rid of all those. So what we're going to do is we're going to multiply the top by the RE and the bottom by the same thing, which is equal to RE in parallel with RO over 1 over R E in parallel with RO plus 1 over GM. And that is my gain, and that is my common collector configuration. And now that we've derived all of these, now we can go over and let me scroll down a little bit. And now here is our table from our sheet. And now every time that we see this configuration right here, once we see this configuration right here, I can use this equation. So once I can put them in these configurations, I can just use these gain equations rather than going through all of these derivations with